All right, so in this video, we're going to take the review of the sigma notation we did in the last video and apply it to finding these little areas of these little rectangles in under curves. So basically, we're going to be finding in derivatives. Okay, so first of all, we're going to find, oops, I apologize for that. First of all, we're going to find the left and right hand sums for the graph of this. Actually, that's the same formula as we did last time, but we're going to go from 0 to 2 this time. And we're going to use 5 evenly spaced subintervals. So unlike last time, I didn't pick something nice. So if I'm going to find my delta x, here's my starting point, A. That's my ending point, B. I can figure out how far that is by finding the distance between A and B, right? A minus B minus A. And then dividing by however many rectangles. That's my n. So I've got my B is 2, my A is 0, and my n is 5. So each one of these, since the interval is 2 wide, and I have to have 5 rectangles, each interval is going to be 2/5 wide. So I hastily sketched in my parabola. That's my formula. It's not perfect and it's not to scale, and I'm sketching in the right-hand rectangles, and you can certainly do this the way we did before. And we can find each of these values, but they're gross. And maybe the sigma notation might be a little more efficient, especially with these fractions. So each of these rectangles has to be 2/5, like I showed up here. And if you see how I drew it, they're each 2/5. I kind of drew the decimals in. But then we have to find these f values also. So we're going to do that by finding the endpoint of each of these. So that's at 2/5, that's at 4/5, that's at 6/5, 8/5, and 2. So those are each of our endpoints. But here's if A is our beginning point and B is our ending point, and our change, our width of our rectangle at the bottom, okay, is according to this formula, and this box is really important. You can find your right-hand endpoint and your left-hand endpoint using these two little guys, these two little formulas here. So I'm going to do my right-hand endpoints over here, and I'm going to do left over on this side. If you can read my handwriting with the stylus, that says left, believe it or not. All right, so I'm going to do my right ones over here. So basically it's saying you're going to start at your A, okay, which is A is 0, right? And I'm going to go up to 2, that's B. And I'm starting there, but on my right-hand side right here, it doesn't start at 0. My first F is at actually 2/5. So I have to add on my delta x. But for my next one, I add on 0 plus 2 of those, and then 3 of those, and then 4 of those, and then 5 of those to get to my last one. So I have to multiply it by whatever subinterval I'm on. So that's how I got this guy right here. I used my formula here. I'm starting with my right hand farthest, I said right hand, excuse me, left hand farthest interval, and I'm going to move all the way over to B, but I'm starting at A, which is 0. I'm going to add on 2/5 a bunch of times to get each of those intervals and then to find each of these F values up here. So this is my X sub I, we call that. This book calls it C sub I. Okay, so it's really just 2/5 I when I simplify that. On the left-hand side, let me change color so it sticks out a little more. You start with your A, but you don't start with adding 2/5. You start right at 0, because on your left-hand side, you're drawing this rectangle way up here, and then here, all the way down, and here all the way down. So you're actually using the left-hand side of that. That starts at 0, then goes to 2/5. You add 2/5 on after that. So you start with A, but you don't add 2/5 the first time. So even though you always start with I is 1, but if I is 1, that first term has to have the 1 subtracted off. So that's where this is from. My delta x is what I got up here. This is delta x, my width of each interval. My A is my starting value. I'm going from 0 to 2. That's the starting amount of the left-hand side of my interval. And then I'm going to add a bunch of those delta x's a bunch of times. This is always I minus 1 for left endpoints because your number, if you went 1 away, you're at the right-hand side of the interval, not the left-hand side of the interval. So you have to subtract 1 off to be back at 0. You want to have 0 for your first term. So if I'm going to write my sums, this is what they look like. Now the algebra on this gets really fun, which is why if you printed them, I left a blank page so you could bleed onto the next page. I'm not sure it's appropriately placed, but you'll definitely want a spot for it. So now to write this formula, I'm going to add up, so sigma, from the first rectangle to the fifth one. So I'm going to make 5 different rectangles, so I have to add up 5 different things. So I1, I2, I3, I4, A5. So A1, A2, A3, A4, A5. Those are going to be our 5 rectangles. And that means I have to add the height of each rectangle. Actually, I'm going to write that actually in words. Height of each rectangle times the width. So what did I figure out my width was? Well, my width is just delta x, right? My delta x is this. So I'm going to actually write that in as a formula first, and then we're going to do the math. Okay, so I'm going to do my delta x, which is really 2/5, and I'm going to write that in a second. But my height is really just my f of whatever the x value is at that term. And I just got done telling you that your book calls it c, so I'm going to call it c. C sub I. Okay, so that's C with a subscript of I. All right, so now let's plug in what we know. We know that our CI is this guy. So we're going to put that in. We're going to put that in. We've got 5. And our sigma. We're starting with 1. We're going to 5. Okay, 5 rectangles. And then we're going to put this C of I into our f of x. Okay, I called it y, but same deal. Okay, I'm going to put in f of x. F of x is negative x squared plus 5. So what is our C of I? I'm going to put in to my f. Well, it's this. It's 2/5 I. So I'm going to put 2/5 I in there. All right, but don't forget I have this delta x out here, which we calculated way up here. We've calculated it's 2/5. Now comes the fun part. Now comes the algebra fun. So you have to actually do your algebra to make your algebra 2 teacher really proud. All right, sigma, I equals 1 to 5. I'm going to multiply out. That's negative 4/25 I squared. Oops, I forgot to write the square. I said it. Plus 5. Now, we just got done saying that you don't need this 2/5 inside of a sigma. You can take out numbers that don't have I in it out front. So what did I do? I multiplied out the squared. I did bring down the 5, but I put this 2/5, I put it out in front because I didn't want to look at it inside my sigma. My sigma is complicated enough. So now I'm changing colors. So 2/5, I'm going to put a big parentheses. Maybe a bracket would be more appropriate. It doesn't really matter. I'm going to think about each of these parts of the sigma, right here and right here, as 2 different ones. And remember, you can take apart sums or differences into 2 sigmas. So I'm going to make that 2 sigmas. So here's my first one, and I'm going to put that negative 4/25 out in the front. I'm going to write the sigma. I'm going to write that it's from I equals 1 to 5. And I'm going to put my I squared in there. Don't forget that little squared. It's hiding up there. Plus, now this part is also a sigma. Sorry, my sigma looks a little funkadunk there. And it's just 5 for that part. All right. So now I'm going to make that black so it looks like it's all together. So I did formulas. I'm going to use formulas for each of these sigmas. I split up using my properties, my sum rules. Now I'm going to actually do the math with these. All right. So I'm going to bring down the 2/5. I'm going to copy down my negative 4/25. And now this next part, I am going to use a formula on. that requires a formula, and that's not the Einstein formula, but the next level up. And that formula, I'm going to do it in red so you can see that I'm changing this part right here into a formula. It's n times n plus 1 times 2n plus 1, all divided by 6. And our n is 5, so I'm going to put that 5 in. So 5 is n, and then 5 plus 1, right? N plus 1, I did that just in my head, 5 plus 1. And then 2 times 5 plus 1, well, that's 11, divide by 6. So that's a formula just for this part of that. All right, plus now the formula for this part is sigma c, right, from 1 to n is Cn. Well, my C is 5 and my n is 5, so 5 times 5 is 25. I think we can do that. All right, and now I'm going to just, I wrote 5 plus 5. That's a bad thing. That's a 5 times 5. I said 5 times 5, though, I hope. So now I'm going to do the math. I'm going to pause it, and I'm going to let you try to do the math. And hope I'll show my steps, so they'll all kind of be there when I'm done. But that way you don't have to listen to me as I do every little arithmetic step. So you see I got 6.48, 162/25. And that's how you find the right-hand sum. Now, agreed, this isn't very efficient for 5 rectangles, even with fractions. I probably would have just done the fractions. However, what if you had 100 rectangles that you had to do, or even 10? Ugh. So this might be more efficient if you had that. Now, I'm going to move this back up to the top, and we're going to talk about left hand. I have to erase a little bit of this because I got it all in the way. Go away, go away. Okay. Now, I don't think we're going to do all the arithmetic of the left hand one. We are going to, however, write out what the summation would look like. Okay. So on this one, we're going to go also, we're going to do 5 rectangles. That's an equal sign. All right. And we're going to do f of xi because those are the heights of each rectangle. Oop, we're going to call it ci. I lied. They're the same. It's just delineating that each value is a constant rather than a variable, and so you don't have 2. And then delta x, right, for your width of your rectangle. So your heights of your rectangles times your width of your rectangles. Now, we figured out the left endpoint here. So on this one, you're doing from I equals 1 to 5. We're doing 5 rectangles. We're going to do f of ci, and this is my ci, right? These are my ci's for each left endpoint. So, or left, it's a left endpoint of each of those intervals. So if I want to find the height, I need to put that into f. Since our f of x was negative x to the second plus 5, I have negative x to the second plus 5, and then my delta x was 2/5. Now, my CI is complicated. It's this guy up here, and my A was 0, so I really should have just written it as that. So really we have 2/5 I minus 1 and squared. Now, I hope you're seeing already that we got to FOIL out that I minus 1. There's a lot more terms when we do this. It's the very same process. It's just a lot longer. If you would like to do this, it is literally in your book. I will also take a snapshot of my work so that you can see it, but it's 8.08 you should get for your answer if you want to do it, but it's not worth everybody listening to on the video. I will take a snapshot and post it with this video so that you can look at my work that shows how I did that and maybe some of my better work for the right hand endpoint, right hand sum rather. Now this one also, I've decided I'm going to let you try on your own if you really want to. I left you space, but it is right in your book. I try to use problems from your book so you could have me and the book to kind of follow along at the same time. And if you didn't understand me, maybe the book would be helpful or vice versa. But these are just tedious if you couldn't tell from the last one, and they're not really the point. So the point is that you have left-hand sums and right-hand sums. We did that on the first set of videos, and we kind of did it here. There's some left-hand sums that are some above rectangles and some below rectangles. So you got to talk about which ones give you overestimates and which ones give you upper estimates. And we talked about also lower sums, and upper sums. So these left sums and right sums have these formulas that we kind of talked about in that last example. You find a left endpoint using this formula, the right endpoint using this formula, where A and B are your beginning and ending points, and that's how you find your delta x's. Now, your lower sum, you can always find, remember, using inscribed rectangles. Rectangles are always below the curve, and it's always, this is backwards. It should be less. I don't know if I just flip-flop them. It's always less, and this one's always more. So my bad. Wouldn't be a Miss Kite if you didn't have a typo of some sort, right? You're gonna miss that so much about me next year. So this one should say less, and this one should say more. All right, now the lower sum you get by taking all the rectangles, the heights, and the widths of them. Well, the width we get by doing this little formula, right? You take your first and your last point and then divide by however many subintervals. But you get your inscribed rectangles by doing the minimum f in every interval. Okay, and the same here. This is the big M. You do the max f in every interval. That says max, believe it or not. Okay, so the best estimate is when you average the left plus the right. Okay, that's the best estimate always. It's also, you can get that using the trapezoidal rule. But the idea is if we take those sums and we said if you make a lot more rectangles, you get a lot better estimation for the area under the curve. So what if you take that limit and make your number of rectangles infinite? Take the limit as the number of rectangles here goes to infinity. So this lower sum we're going to take to infinity, which this is the formula for. We're going to find all the heights and all the delta x's, and we're going to add up an infinite number of them. Okay, you have to use your imagination for that. Same thing with all the big ones. They should turn out to be the same. The upper and lower sums should be getting closer and closer together, because the more rectangles you have, the less area you have outside and the less area you have inside. So this is kind of squeeze theorem reminiscent, isn't it? So you find the area under a curve by taking the limit as n goes to infinity of all these heights of an infinite number of rectangles and all the widths of those infinite number of rectangles. Now remember, you can't actually get to infinite number of rectangles. We're approaching infinity. So does it approach a number? You find your delta x using this little formula. You find your ci's. We use the right-hand endpoints because they're way easier. Remember that example where I'm like, it's too tedious to even do? And remember that your ci's between your first and your last x. All right, it's somewhere in the interval. This is the left-hand point. That's the right endpoint on the interval. That's somewhere in the interval. It could be at one end or the other. In fact, we made them all at one end. All right, so if I'm going to do that for this curve, x to the third, between 0 and 1, we can use our limit formula. And this is going to be extra fun. So our delta x, we need to do b, and that's a, minus a, over your number of rectangles, but we don't know. We're going to take that to infinity, so we're going to call it n. We don't, it's n number of rectangles. Okay, so that's 1 over n, right? And then to find our ci's, we're going to do this guy. We're going to take our a plus I times delta x we just got up there. Okay, so I literally just plug that in. This is my delta x, so I put it in. I found it right above. All right, so our ci's are I times 1/9, 1/nth, excuse me. So now I'm going to substitute this in over in my area formula. My area is equal to the limit as n goes to infinity. And yes, this is a lot like when we had to do these awful limits for finding derivatives, and then all of a sudden we found shortcuts and we went, oh my gosh, that's so much easier. Thank goodness we have a shortcut. Yes, I'm going to teach you the shortcuts. All right, so we still have to do a sigma from I equals 1 to 5. And then we need to do f of ci. I don't need to write the f, sorry. F of ci, what is our f of x? It's this guy. So I need to do x to the third, right? Our ci to the third. Ci is 1 divided by n times I. I just realized over there it looks really funkadunk, so I'm sorry. Times delta x, we found that over here. It's 1 over n, right here, right? Delta x. Okay, and now it's just algebra. It's gross algebra, admittedly, but it's algebra. All right, so limit as n goes to infinity. And then we're going to do our cube. Okay, yeah, you got to write all that down. I know it's a pain. That's 1 divided by n to the third times I to the third times 1 divided by n. So these n's come together to be n to the fourth, right? Oops, that's an m, not an n, isn't it? Let's try that again. N to the infinity. And that they don't have an I in it, so I'm going to bring those n's out in front. But then I'm doing my sigma from 1 to 5 of an I cubed. Now that's another one of our wonderful formulas. Okay, so you have to go back and get that formula. I'm going to pause and move this because, fair warning, I'm just going to move it. I warned you. All right, so we need to use that cubic formula. So the cube formula, if you do the sum, it is actually n squared, n plus 1 squared, all divided by 4. And you can look that back up on the previous pages, not in this video, but previous pages of the notes from this same note packet, but different video 1. So I'm going to substitute that formula in. Limit as n goes to infinity. I'm apologizing for my already bad handwriting. It's even worse now with the iPad screen. But now here comes my formula. I know how to do this. I put it right over here. N squared, n plus 1 squared divided by 4. I don't know why I felt compelled to write it over here to just immediately copy it there, but I guess I won't do that on the next one. That was goofy. All right, now it's just algebra again. I see that some of these cancel. I'm going to cancel. There's going to be 2 left on the bottom. So then I've got the area, the area equals the limit as n goes to infinity. And this is going to find the exact area, by the way, because now we've got an infinite number, theoretical infinite number of little rectangles. And that's a 4n on the bottom, right? I'm going to bring that 4 over and combine it with that. So let me erase this infinity. It looks really crowded. And then this guy is on top, so I don't really need to write that n. So I'm going to write n plus 1 squared. Now I just need to take the limit. And you're going, ugh, I don't want to take the limit. I've got an infinity over infinity. And I hope you're going, l'hôpital, you're going to come in, l'hôpital. I put my eye in the wrong spot. L'hôpital, you've got an infinity over infinity. You can take the derivative of the top and the bottom. Okay? So this is the same thing as the limit as n goes to infinity. And now I'm going to use the chain rule on the top. Bring down the 2. Change it to a 1. And the derivative inside of here. The derivative inside of here is 1, so I'm just not going to write it. So brought the 2 down, change it to a 1. Derivative inside is 1. I'm not going to write it. It's out here technically. And then the derivative of the bottom is 8n. And so you put infinity in, and you get infinity over infinity again. So you have to, do more work. But it's infinity over infinity. So l'hôpital. Okay, so limit as n goes to infinity. And now I'm going to take the derivative of the bottom because it's easy. And the derivative of the top, I'm just going to use, this is 2n plus 2, so it's 2. That's 1/4. The area under the curve is a 4th. Isn't that cool? And there you have it. We used sums, and it wasn't nearly so bad as that last one where you had, and you don't have to add up 1,000 of them. You don't have to add up 5 of them. You don't have to do all those little fractions. You have to use algebra. It was brought to my attention that I actually miscopied this. See, that's an n, and I copied it down as a 5, probably from the last problem. I just had it in my head. So there are 3 places you need to fix that in your notes. So if I confused you, I apologize and fix it now. So I'm going to do this last one, and there's one more in your book that uses y, and I'm not going to do that one. I decided I think we can leave that as an exercise for later. If we were doing solids of revolution, we would do it, but since our year got cut so short, we will not be doing that. we're going to talk about finding the area bounded by the graph of this parabola, 4 minus x squared, and the vertical lines 1 to 2. I'm going to sketch in a little picture because pictures are good for me. So we're going to find the area of that little shaded region right in here, and we're going to do it by finding an infinite number of rectangles instead of all these little fractions or something. So here's our A, here's our B. We're going to do an infinite number of rectangles, so we're going to call it n and then take the limit as we go to infinity. So our delta x is going to be B minus A divided by n. That's 1 divided by n like it was last time. Our CI, remember, we take A, which is 1 in this case, plus I times delta x. So I'm going to write that 1/nth out in front. I wish I hadn't. It doesn't look good there. So you're going to have I delta x. Okay. Remember, this is not the imaginary number I. It's a different kind of I. It's just a counter. Literally, it counts things. It counts how many terms. Counter. Now, our area then, we're going to do the limit as we take our number of rectangles, n is the number of rectangles, to infinity. We're going to add up all those little rectangles from 1 to infinity, because n is going to infinity. And we have to do our heights of our rectangles and our widths of our rectangles. Our width, we said, were 1 over n. Okay? Our heights have to do with our formula. So we have to do 4 minus x squared, but we have to put our CI in it. Our CI is that thing, and I did not leave enough room, so I'm going to scribble that out, put it bigger. I'm going to do 1 plus I divided by n. Now, that whole thing is multiplied by 1 over n. Now it's just algebra. The algebra is a little funky, but you can do it, okay? You've got this. It looks gross because there's all kinds of alphabet soup and math symbols, but you got this. All right, so I'm going to pull that 1 over n out in front because it doesn't have a single dang I in it. It can just bloop, go right out in front of here. I don't need it. So I'm going to move it out of my way. I do that a lot with integrals and antiderivatives. That 4 is just a 4 minus, let's see, I'm going to FOIL that out. I'm going to FOIL it out. Let's see, that's 1. But I better put my parentheses. And then plus 2i divided by n, because I combine like terms, okay? If I do 1 plus I over n and 1 plus I over n, I get 1, and then I over n and I over n again, so 2i over n. So I have plus I squared divided by n squared, because they're both squared. It's I divided by n, quantity squared, so I'm going to write it as one big quantity like that. Now, we're going to take the limit. I'm going to just keep doing the algebra. You can do this. I'm going to bring down the 1 over n. I'm going to do the sum for each part. So I'm going to use that sum rules where you can have a plus b, where I split them up so into many sums. I think that's easiest. Okay, apparently I'm changing colors. So let's do that. 4 minus, now I'm going to distribute my negative at the same time, minus sigma I equals 1 to n of 1 minus sigma 2i divided by n, and that goes from 1 to n. And then minus, because I'm distributing my negative, minus sigma I squared n squared. Now, we just have some algebra to do. We can totally do this. This is equal to the limit as n goes to infinity of 1 divided by n and a big parenthesis. I really should put brackets around that whole thing because it's 1 divided by n. It's all that sum, and I split the sum up into several sums. But remember, this part has a formula. That's that sigma c, and that to an n. So that was cn from our sum rules, and our c is 4, and our n is n, so 4n for that. And this one right here, same deal, minus, and that's 1 times n, so that's 3n right there. And when I combine like terms, I'm going to do that in the next step. This next one, I'm going to pull that 2 divided by n out in front, and just the I is left in there, okay, and that's from, I get really tired of writing all these, and so I know you do too, but yes, you have to write them, minus 1 divided by n squared, that's my husband closing the garage door, so sorry. All right, 1 divided by n squared, I equals 1 to n, and I see that I forgot that up here, and I keep bumping my little, a button on my tablet, and it keeps doing funky things, so I'm hoping it doesn't do that again. And that's an I squared in there. Okay, now I'm running into all this stuff over here, so we don't really need this anymore, so I'm going to erase it. I'd like to save it there, but we don't really need it right now. So, next, oops, I forgot my big parentheses, so let's put that on. Now we're down to pure algebra. Limit as n goes to infinity, 1 over n. Okay, algebra plus limits. That is 3n. I'm going to combine that, minus 2 divided by n, and then this guy has a formula. That's Einstein's formula, so it's n plus 1, n divided by 2. I put them in reverse order. It's n times n plus 1 divided by 2, but same deal. Minus 1 divided by n squared. And then I squared also has a formula, and I'm good at forgetting this one. So n plus 1, 2n plus 1, divided by 6. I have to look it up too, don't worry. I'm not judging if you do, especially since you haven't used it nearly as much as I have. Okay, 1 over n. Now, I'm going to actually distribute that 1 over n instead, so I get rid of some stuff. So I'm going to start distributing this in. 1 over n times 3n, now, well, that's just 3. Minus. Now, if I multiply that together, first of all, I notice these cancel and these cancel. So I'm left with n plus 1 divided by n. Minus. Now I'm going to distribute my n plus 1 over here, but first I'm going to cancel. I notice those cancel when I distribute. So I'm left with n plus 1, 2n plus 1, all divided by 6n squared when I put these pieces together. And I'm going to move the screen, so it's going to look a little funky. I'm trying to do it slow so I don't make you seasick. Now, we're on the home stretch. So, limit is n goes to infinity of 3 minus, now I'm going to just take the limit of each part, because I can do the parts easily. The limit is n goes to infinity of n plus 1 divided by n, minus the limit as n goes to infinity. My children are getting ready for bed. I need to go help them soon. N plus 1 over 6n squared. Okay, now, almost there. The limit of 3 is 3. There's no n in it, so it's just 3. That part's done. Yay. Now this next part, when n goes to infinity, we put infinity in, right? You'll substitute first, cry later. Infinity over infinity, uh-oh. But you have to do more work, but that's a L'Hopital. So you can use L'Hopital's rule and just take the derivative of the top, 1, and the derivative of the bottom, 1, and then take the limit of that new thing, which is just 1, so we're going to do that in the next step. And the same thing here. If you put infinity in the top of this, you get infinity, right? Infinity times infinity, infinity. And again, infinity times infinity, infinity. So you can use L'Hopital's rule. So the limit as n goes to infinity. And now I'm going to take the derivative of the top and the derivative of the bottom. The bottom's easier, 12n. And the top you have to use product rule, or you have to FOIL out first. I think the product rule is easier this time, so derivative of the first, leave the second be, plus leave the first, take the derivative of the second part. Now, I see that I still get infinity over infinity, but these parts are 3 and 1, like we said before. The first part is 3, the second part's 1, limit of 1 is 1. But this part, we still get infinity over infinity. I see infinity, right? It's all positive. It's just all infinity up there. 2 times infinity plus 1 is infinity plus 1 times 2. That's all still infinity. Infinity over infinity, we have to do more work. L'Hopital's rule. Now, so I'm going to do L'Hopital's rule on that. And I'm not going to bother. The bottom's just 12. I'm not going to bother doing too much. I can just see that that's 2 for this first part, right? Because if I distribute 1, derivative of 2n is just 2 plus 0, because the derivative of 1 is 0. And when I distribute that next part, it's plus 2n, so the derivative there is 2 plus 2. The derivative of 2 is 0, so I get 4. So this whole thing is 3 minus 1, which is 2, plus 1/3, 4/12, 1/3. So you get 1 and 2/3, or 5/3, either way. And that's the area under the curve that we talked about way up here right there. Now, yes, this is tedious and long. And yes, there are easier ways to do this. And yes, we are going to do those shortcuts and we're going to do them like ASAP. So we're going to talk about how this is really just an integral. And we're going to use that. And that funny little S, there's a reason it's an S. It's a sigma. It's a sigma. It's a sigma because this is a sigma. It's a sigma where you're taking the limited and goes to infinity of all these little infinite number of rectangles. That's where that symbol comes from. So the next video talks about how you do that to find nice, easy formulas for geometry, but then take that to the next step and use it to find area without doing all this crazy long arithmetic. You use antiderivatives, and fast, here they come. So stay tuned. That said, I made a mistake down here, right here on the very bottom. I wrote a plus right here, and it should be a minus. And so you get the answer I still got, I just miswrote it. So FYI, but stay tuned for the next video. I squared, I'm back to you.